Welcome back to Electronics. This is Dr. Robinson. In this lesson, we are going to work out a low-pass filter design example. Let's look at how we would design a Butterworth second-order low-pass filter. Now, once I've told you it's a Butterworth filter, we know that that implies that the quality factor of the second-order transfer function is equal to 1 over the square root of 2. And I want to design this filter so that we have an F0 of 1 kilohertz. And I've chosen to use the special case 1 equations for the low-pass filter. And I've also chosen to simplify the equations further by making this assumption that R1 is equal to R2. Now, we can write that C1 is equal to Q, our 1 over root 2, times omega naught, in terms of F0, is 2 pi F0, times 1 over R1 plus 1 over R2, but these are equal to each other, so I can write that as 2 over R1. Then C2 is equal to 1 over 2 pi F0 times 2 R1 times the square root of 2. Now, knowing that it's harder to find capacitor values because they have 20% tolerances than it is resistor values, the way I solved for C1 and C2 was to look at the available resistors that I had in the resistor bins in the laboratory and choose different values of R1 until C1 and C2 were close to values of capacitors that I had available to me. So trying out different Rs, I reached the conclusion that by letting R1 equal 1 k ohm, a resistor value that's found in every resistor bin in existence, I get C1 is equal to approximately 0.11 microfarads, and C2 is approximately equal to 0.22 or so microfarads. Well, in my 20% capacitor bin, I can choose a 0.1 microfarad capacitor, and I have available a 0.22 microfarad capacitor. So if I implement the circuit using these values, R equals 1K, both R1 and R2 equal to 1K, C1 equal to 0.1 microfarads, and C2 equal to 0.22 microfarads, I get a circuit topology that looks like this. Both 1Ks, a 0.22 and a 0.1. And here you can see that I've set the gain equal to 1 by making this resistor a short circuit and the resistor that was here an open circuit. The simplest way of making the gain 1. Once this is a short circuit, the value of this resistor doesn't matter, but the best solution is to just leave it out because that makes the circuit a little less complicated. Now, if we plot the Bode magnitude plot for this circuit, we get this red curve here on log-log scales. You can see that, as expected, it is a low-pass filter. It has an F0, or cutoff frequency, of 1.12 kilohertz. And the reason this isn't 1 kilohertz is because my approximations in choosing the capacitor values. Now, we would expect this slope, because it's a second-order transfer function, or a second-order filter, to have a slope of -2 decades per decade. And we can verify that. Let's look at this decade increase in frequency. So in moving from 1 kilohertz to 10 kilohertz, we increase by a factor of 10. And in doing that, we decrease the magnitude of the transfer function from 1 to 10 milli, a change in 2 decades in magnitude. So from 10 milli to 100 milli to 1 is a factor of 100, or 2 decades. So we went down 2 decades for this 1 decade increase in frequency. So in summary, during this lesson, we designed a second-order low-pass filter using the design equations that we've talked about in previous lessons. We looked at some practical design considerations, and we examined the behavior of a simulated version of our designed filter. In our next lesson, we will look at a filtering demonstration where I demonstrate for you, using active filters, the extraction of particular frequency components from a signal. So thank you, and until next time.